So welcome to this brief tutorial on FlexParamCurve. My name is Steve Oswald and I'm going to guide you through a couple of examples that illustrate the main functionality of this R package. And you can follow along with the code that's posted on the Methods in Ecology and Evolution website, and that will allow you to see some of the options that you can choose for the different functions, because we're going to go through fairly fast. And we're going to be using the data object penguin data, which is data from blue penguins from Phillip Island, collected by André Kiragier and colleagues. And it's actually discussed in a separate video in our introductory video. Now I'm going to run you step by step through two scenarios that might motivate the use of FlexParamCurve. First off, let's say you want to use nonlinear mixed effects models on your field data, but you haven't yet determined the type of nonlinear curve that best fits your data. And so this is where the model selection routines in FlexParamCurve come in. First off, obviously install the package, and once you've done that, just load the library, and we're going to use the penguin data object. Here, this next command you don't actually have to use here, but with your data, if you need to use it in nonlinear mixed effects models, best to use it as a group data object, and there's some example of how you might do that. The next three commands here again, I'm just using them to subset the data. Those are the band numbers of the chicks I'm going to be using. I don't want to use all the data because the routines will take a long time, so just by subsetting it, I'm going to speed it up a bit. I'll show you what, so I created a new data object, my data. I'll show you what that object looks like by plotting in the lattice package an XY plot or a lattice plot. And there you can see those are the band numbers of the 5 chicks, and that is their ages and their masses. So these are the data that we're working with, and they show obviously a nonlinear relationship. So now run the model selection routine of your choice. I usually prefer PN model compare, which ranks models based on minimization of penalized root mean square error. But I also recommend running PN model select step, which is a backward stepwise routine, and each give slightly different results depending on the variability within your data set. So we run PN mod compare, and there's effectively 4 required arguments: the X variable, the Y variable, and the grouping variable. And also PN options, which is the name of an object to save your options and your fitted parameters in. The grouping variable is required for multi-level data. Now, if you don't have multi-level data, i.e. you don't have repeated measures from the same individuals, which is usual for nonlinear mixed effects models, obviously. But if you don't have that, just specify the grouping level as a single number repeated for the length of the data set, and that will give you effectively a nonlinear least squares fit for each of the model selection routines. And then, of course, we wait. So the first thing that happens is if you've selected a PN options object that doesn't exist, in this case we have, it will attempt to run the function modpar to produce one. So this is the object that has the fitting options and any default parameters in it. And the details that are given there, but basically it's trying to fit an LS object or a workaround for an 8-parameter curve, and if the 8-parameter fails, then it tries to fit a 4. In this case, the 8-parameter is successful just by using the getInitial routine. The second part of this is there are 32 models available in FlexParamCurve, and to fit all of those would take a long time. So we halve the work by just fitting 16 of them. We decide straight away whether the curve needs a variable or a fixed shape parameter, the first part of the curve. And in this case, a fixed one is most appropriate. So we fix that parameter, and then we fit 16 models that have that fixed parameter. And then finally, it starts fitting all 16 models. And you see that errors come up. This isn't surprising, because in this case, there's 7 parameters estimating, and that's likely to be more parameters than are needed for these fairly simple nonlinear curves. So in these cases, for each individual, there's 5 in the data set, attempting to fit them through NLS list as an individual NLS fit for each of those data sets. And in the case for the first model, obviously none of them fit. Um, and then for the second model, we get a few successful fits too. And so now we wait, and if you have more than a few levels, I suggest you take a nap or go grocery shopping or maybe go to the pub. I'm not advocating any of these particular solutions, but it's going to take a while. And why is that? Well, you can imagine if you have 150 individuals in your data set, which is not unheard of, you've got 16 models to fit 150 times, and during the routines, there's at least 3 optimizations. So that's a lot of hard work that you've just missed out on. Okay, so now it's finished, and the thing you'll notice is it lists at the end of the fitting which models fit and which did not. And then we can actually take a look at the output of this mod compare routine. And there's 2 tables, and I apologize for the small screen. The first one has the following 6 columns, but we'll just concentrate on a few of them. The first column is listing the models by name. You can find a detail of how many parameters each one has in the help files and also in the paper. Basically, they're ranked by the function, by minimizing the ranking function value, which is the penalized root mean square error in this case. And you can see RSE is actually the root mean square error unpenalized. And the penalization just works by basically accounting for the fact that models that fit fewer individuals in the data set will naturally show less residual error. So we penalize those, so you end up with a model that's compromised between a better fit and also a more general fit. You see these top 3 models fit all five individuals in the data set, and the first model fits them with the least error. So that's the best model in this case. So, and the second table produced here is just shows p-values for extra f sum of squares tests between nested models. And if a model with more parameters has a significantly better fit, then it should be preferred. But that's just for more advanced use if you are interested in that. So let's now compare those results with backward stepwise selection using pn mod select step. Again, there's the 4 arguments. In this case, I've added an extra argument, existing is true, and this way any of the NLS list models fitted for the previous model selection will not need to be refit, so we'll fit far fewer and it'll take less time. Okay, so now that's run and it's gone through the 6 steps of backwards model selection. And so let's look at the output, and for each step it shows you the best model at that step, and you see that model 22 became the best model and stayed the best model for most of the steps. And in fact, it's actually preferred over model 31, which is what mod compare actually said was the best model. And the reason for that is if we actually look at mod compare, just run mod compare again, just not run it, but look at the output, you can see that Richard's R22 actually only has 2 individuals fitted, so it's suffering from a lack of generality, whereas 31 is preferred if you want more levels fitted. Obviously, R22 has much lower root mean squared error. So now we know that model 31, which actually just has a single asymptotic parameter for the second part of the Richards curve, the second part of the double Richards curve, is the best model for the penguin data. So in our second scenario, we're going to now suppose we have our best fitting nonlinear curve, but we want to use this to plot this and look at it, and also to run nonlinear mixed effects models. Well, how do we do this? Well, first off, let's have a look at our best fitting model, which is the R31. Again, I should make it a bit bigger for this. This is just looking at the model. It shows you the coefficients, degrees of freedom, standard error, etc. And you can see straight away that all 5 individuals have been fit. And there are 4 parameters, because the first shape parameter is fixed, and there's only 1 parameter, the second curve. Then, if we want to do a plot, I'm just going to use shortened plot names. It's just because my level names are kind of long. First, you want to extract the coefficients from that model, and then just use XY plot. And you can look at the contents of this XY plot. It's it's using a panel function to both plot the data and then plot the best fitting curve from NLS list for each individual from that sub-coefficients, and then also a curve across individuals using NLS. And it actually takes that out of the saved options, which are basically NLS fits to produce the mean parameters across all the data. So let's go ahead and plot XY plot, and you see the XY plot is actually using Posner-Richards equation, which is like the self-starting SS Posner-Richards, but it's just for plotting. You can look at that in the code provided. Now, I'll just make this larger so you can see what's going on. And there's again the 5 individuals with their data, this time in gray. And the black line is from NLS list, and the dotted gray line is from an NLS fit across all levels. So you can see obviously the individual level fits fit better than one across all levels. So it's a better summarization of the data. So finally, we want to fit a nonlinear mixed effects models. We can use the best fitting model R31.list as a starter and fit a nonlinear mixed effects model in NLME using the NLS list object. But we actually have to refit it in this version. And one of the easiest ways to fit these models in FlexParamCurve is to use the data object Posner-Richards calls, and I'll show you what that looks like. It's a list of the 32 different models listed by the ones where M is fixed and the ones where M is free, and these are just the calls that would run the fitting process, the self-starting fitting process. So we want to refit model 31 here. So first we want to extract it. That's what I'm going to do with this code. Just extract that model. And if you want to have a look, mod to fit, it's just as a text. There it is. But obviously we don't have a mass variable, we don't have an age variable, we have weight and chick age. So there's a bunch of different variables we want to change. We just use the sub function to sub out those with our actual options, and then just fit that list model again. And so now that's fit, and it was just by evaluating the past text of mod to fit that I did that. And if we just look at that object, you can see it looks the same as the object that was produced by the model selection routine. So let's just go ahead and fit the nonlinear mixed effects model. And this fits really fast. I'm using a diagonal matrix to speed it up, but it fit really fast. So let's just have a look at summarizing that model. And you can see the nonlinear mixed effects model fitted with that formula with the self-starting Posner-Richards curve and the 4 different variables. And that's all there was to it, really. So hope you've found this tutorial useful, and I hope you get some use out of the package. Thank you very much.